Hello, y'all. Welcome to lesson 59 of my DB chemistry curriculum. Today we're doing structure 2.2.4. The position of a compound in the bonding triangle is determined by the relative contributions of the three bonding types to the overall bond. At the end of this lesson, we'll be able to determine the position of a compound from its electronegativity data, and we'll also be able to predict properties of compound based on its position in the triangle. So, with this said, we're going to kind of talk about that continuum we discussed in the previous lesson, because we already discussed that we have this bonding as a continuum, meaning the properties kind of relate to one another, and the way that these bonds interact also kind of relate and are shift one way towards another. But with this bonding triangle, we can now assign numerical data to this continuum, which we love to do because then it gives us a more concrete way to do it, or a concrete way to look at a spectrum or continuum. So as we assign numerical data, we have to figure out the parameters we want to use. And it turns out that if we use something called electronegativity, it works out pretty well. Whoops. Electronegativity. And the reason we're going to use electronegativity is because we already know this is basically an indicator, indicates how atoms will attract or share electrons. And that way we can look at the difference in bonding as a difference in the way that atoms will want to pull on the electrons in the bonds. And we remember from all of our bondings, we are still just talking about moving or sharing or transferring or delocalizing electrons. So electronegativity kind of works out great for this. When we consider electronegativity, we have to consider the two different types of elements. So we have metals, which they tend to lose electrons. They don't attract, or they have a low attraction to additional electrons. So all in all, these generally tend to have very low electronegativity. Meanwhile, our nonmetals are kind of the exact opposite. Nonmetals tend to gain electrons, and they have a high attraction to additional electrons. And that second point, the attraction to additional electrons is just kind of another version of our electron affinity. So these have high electronegativity. And now we can describe all three bonds and kind of relate electronegativity to those bond types. So we can do this in a chart because the charts always kind of help you visualize things a little bit better. At least they do for me. So if we look at our bond type and we compare it to the elements in the bond, we'll know a little bit something about the electronegativity. So let's start out with ionic. Ionic uses metals plus a nonmetal. And between the metal, we have a low electronegativity and a high electronegativity. And altogether, what we're going to see is basically a large difference in electronegativity. And we already talked about this one once before. We looked at a scale that kind of went zero point 0.4 or 0 to 0.4 to 1.9 to 4. And on this side, we had ionic. And on this side, we had covalent. And we're just kind of looking at that whole range, that 1.9 to 4. This is a large difference in electronegativity that kind of shows an ionic. The only difference is now we're going to be looking at this as a continuum over multiple types of bonds instead of just the two of ionic and covalent. But moving on, we'll talk about covalent here. So covalent bonds are nonmetal plus a nonmetal, and they both have high electronegativities. And so together we're going to have a high average electronegativity. So like oxygen with oxygen is going to have an average electronegativity of 3.6 because each of them are 3.6. So generally when we create these covalent bonds, overall the electronegativity average is going to be pretty high. Remembering that our scale only goes from 0 to 4, so anything above 2 is a very high average, honestly. Um, and now we have metallic. Metallic is definitely a metal plus a metal. These both have low electronegativity values, and here we're going to have a low average electronegativity. So this is what we can base our bonding triangle off of. And this triangle will be in all your DP Chem data booklets. Hmm. That picture is a little hard to see. Let me just take a moment to fix it. All right, so here we have our bonding triangle, or what's actually also known as the Van Arkel cat Kettelar Kettelar triangle for the scientists. And what this does is it has not two axes, but three axes that we can go off of, as well as shaded areas that divide our triangle and allow us to identify properties and bonds and character of these individual combinations. So up here on our y-axis, we have the difference in electronegativity. You'll notice that as the difference in electronegativity increases, we go from covalent to polar covalent and ionic. And you also notice metal heads towards ionic as well. Over here we have our on our x-axis the average electronegativity. A higher average electronegativity relates to covalent molecules, while low average electronegativity relates to metallic compounds. And then because covalent and ionic kind of exist in that continuum that we've been talking about, we actually have percent covalent and ionic character. So something right here in the polar covalent range might be about half covalent, half ionic in terms of the character, the way it behaves. So with that triangle, we can start creating distinctions for bond type. However, we have to still divide polar and nonpolar covalent because they act so differently and there is such a large difference in that electronegativity. So um, moving from here, the best thing to do is just take some examples. So let's start off with just something like magnesium oxide. Magnesium has an electronegativity of 1.3. Oxygen has an electronegativity of about 3.4. These are all values from the data booklet. Magnesium oxide is a very common compound that we find on Earth, and we can kind of start saying how that bond generally affects it or what that bond acts like. One thing we can do before we really start is we know a metal plus a nonmetal, this is probably going to be ionic, but its properties may drift towards the covalent or may drift towards the metallic side, and we won't really know until we start doing the bonding triangle calculations. So we'll start out with the average electronegativity. So what we'll do is we'll sum the electronegativities, which is 1.3 plus 3.4, and divide by 2. This is going to give us 4.7 over 2, which is going to give us an average electronegativity of 2.35. So somewhere on this line. Maybe we'll scooch it a little over. All right. Then for our next one, we'll do our electronegativity difference, which is just the absolute value of the difference, but I'm just going to put the big number first so that I don't have to do absolute value. And we find that our difference is 2.1. So when we draw that line on our table, we can see that we're smack dab in the middle of the ionic. This is therefore going to be an ionic bond. You'll notice that even though it's an ionic bond, it does have a little bit of covalent character. It's about 70% ionic, but it does have about 30% covalent character, uh, which doesn't mean it's covalent. It's still firmly ionic, just something of note. Now, when we look at other compounds found in the Earth, like other oxides, like maybe silicon oxide, or silicon dioxide, apologies, uh, we can do the same thing. This is still 3.4, and this is 1.9. And we know that our electronegativity difference, or sorry, our average will once again just be 3.4 plus 1.9 over 2 and give us about 2.65. And our difference is just going to be 1.5. I'm just speeding the math up here. And so with silicon dioxide, we can make our new lines. So 2.65 and 1.5. This is now a polar covalent bond. You'll notice though that it is about 50-50 covalent ionic, which means we're going to start noticing that it acts more ionic than something that would be down here at the bottom, than like an oxygen molecule. Silicon dioxide might be hard and brittle, like glass, while other covalent compounds like glucose does not act like that. So uh, this is still going to be about 50% covalent. And while this is a polar covalent, it does have some properties similar to ionic. And this is what we mean by this continuum. While we have very clear divisions, as compounds get closer to boundaries in the bonding triangle, they will have more intermediate properties. So we could do a couple examples like within covalent networks. Covalent networks, they generally tend to have very low difference in electronegativity, and so we kind of hang out on the bottom line here. And so one example might be silicon. Just pure silicon. That has an electronegativity of 1.9. Pure silicon exists right here on this metallic covalent boundary. And turns out it has very similar properties to a metallic bond. Pure silicon is sometimes conductive. It has conductivity when we need it to. This is why it's used in computer chips. It's very hard. It is almost metal-like. It is shiny. However, it still bonds as a covalent network, but it is a covalent network bonds. So it seems very metal-like while still having this covalent bonding structure, which shows you that this bonding can kind of exist right in these in between where we're not really sure if it's metallic or ionic or covalent because its properties will be across both kinds. So this triangle is going to help you out kind of determine where properties are going to lie. And so you just have to be confident in your usage of it. So I hope this helps and have a great day.